GCN and GraphSAGE both pass messages, but they learn from neighborhoods differently. That difference changes the embeddings you get. This is the setup you'll be able to run after this, which compares two ways of mixing neighbors on a graph and reports the better model. I'm Professor Pi, teaching AI foundations with simple Python. Graphs show relationships. We use graph neural networks when node features and connections both matter. In practice, that means social networks, molecules, citation graphs, or product recommendations. The core challenge is this: each node should learn from its neighbors without losing its own identity. Graph convolutional networks lean towards smoothing. GraphSAGE aims to preserve local signal while still aggregating context. PyTorch Geometric is a compact library that gives us building blocks to test these behaviors quickly in Python. At a high level, GCN averages neighbor signals with a normalization that encourages smoothness across the graph. GraphSAGE concatenates a node with an aggregate of its neighbors, which can keep node-specific signal stronger. Imagine two connected users. GCN will make their profiles more similar by averaging. GraphSAGE will let each keep a distinct fingerprint while still borrowing local context. Strength and weakness trade-offs show up in downstream tasks like classification. We will build a tiny toy graph, run a single GCN layer, compare GraphSAGE embeddings, swap aggregation to max, and then run a tiny classification check. This keeps the experiment focused. The code runs fast and produces numbers you can inspect as you follow along. First, we create a tiny graph to inspect neighborhoods and features. This snippet creates a small graph in PyTorch Geometric and reports its size. The tensor X holds 2 input features per node, so you can visually trace how attributes move through layers later. The tensor edge index encodes directed edges as source and target rows, forming a simple chain with a shortcut to make neighborhoods non-trivial. The data object wraps features and edges into a single container named data that downstream layers consume. Because everything is in memory and tiny, it runs fast and remains easy to inspect. The printed counts confirm the structure you will reuse across the next steps. You can open this data object and see node counts and edge lists before you run any model code, which helps debugging and intuition. Next, we run a single graph convolution to see neighborhood smoothing. This example applies a single GCN conv layer from PyTorch Geometric to the toy graph to demonstrate neighborhood smoothing. The GCN conv object maps 2 input features to 4 hidden features, while mixing each node with its neighbors using degree-normalized averaging. Passing data.x and data.edge index into GCN produces hidden vectors HGCN, and ReLU keeps only non-negative activations to reveal the smooth's magnitude. The variable GCN mean summarizes overall activation strength by averaging all hidden values. Increasing out channels increases capacity, and typically raises this mean slightly after ReLU, while fewer channels constrain expressiveness. Watching the mean shows how much signal survives the smoothing operation and gives a quick sense of whether the layer collapsed distinctions or preserved variance. Now, we compute GraphSAGE outputs and compare pairwise geometry to the GCN result. This code contrasts GraphSAGE and GCN embeddings using PyTorch geometric layers on the same graph. The SAGE conv layer with aggra equals mean learns neighbor aggregation by concatenating a node with its average neighbors, often preserving more node-specific signal than GCN. After computing HSAGE, the function cosine similarity measures how similarly nodes 0 and 1 are embedded by comparing the angle between their normalized vectors so values near 1 mean high alignment. The variable sGCN holds the same comparison for hGCN from the previous step, and gap reports how much GraphSAGE shifts this pair's alignment relative to GCN. Larger positive gaps imply Sage pulls the pair closer. Negative gaps indicate the opposite. Seeing this gap helps you intuit how aggregation changes pairwise geometry. Next, we swap GraphSAGE aggregation to an extreme operator and observe the effect. This snippet swaps GraphSAGE's aggregation from mean to max in PyTorch Geometric to show how the operator changes embeddings. The SageConv object with agger equals max takes the element-wise maximum over neighbor features, emphasizing salient signals instead of averaging them. Computing hmax and then cosine similarity between nodes 0 and 1 yields smax, which we compare to the earlier mean aggregated sSage. The variable shift captures how much the similarity moves when aggregation changes. Increasing feature dimensionality can dampen or amplify such shifts, depending on redundancy in the hidden channels. The printed shift highlights how a simple aggregation choice can realign neighborhood influence and change which node traits dominate the embedding. Finally, we test how those embeddings work for a tiny downstream task. This example tests embeddings with a tiny node classification baseline using PyTorch geometric outputs. The vector y holds binary labels, with train carrying a few labeled nodes and test carrying 2 unseen nodes. The function normalize creates unit length embeddings, so cosine is equivalent to a dot product. Class centroids CG and CS are computed from training nodes in the GCN and SAGE spaces, respectively. Predictions for test nodes select the centroid with the higher similarity, and accuracy is averaged per model. If you add more channels or deeper layers, centroids may separate further and boost accuracy. The printed accuracies show which aggregation produced more discriminative embeddings. If you map this toy experiment to a real project, the train labels become your labeled users or molecules, and the tiny graph becomes a sample subgraph from your full dataset. The same comparison tells you whether smoothing or concatenation yields better separability for your labels before you scale experiments. Recap. First, GCN smooths by normalized averaging and tends to homogenize neighbors. Second, GraphSAGE concatenates node and neighbor summaries to keep node identities stronger. Third, choice of aggregation matters. Mean, max, and similar operators change geometry and downstream separability. Next step. Run the same pipeline with more hidden channels and 1 extra layer, and measure how accuracy and pairwise gaps change as depth and width increase. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.